Hi, everyone. I am Matteo Collina. I work for a company called nearForm. There will be a nice logo in a couple of slides at the end of it. Well, this talk is all about speed and how to write fast Node code. In fact, all this, well, it's not about Spaceball, and it's not about light speed. It's about Ludicrous speed. What does it mean? Well, we'll see in a moment. All this starts back in 2013, when I was at NodeConf, an amazing conference, by the way, speaking about MQTT and MQTT.js, a library that I wrote. And in particularly, I presented my MQTT broker called Mosca, which is open source, as you can imagine. And well, I said it was fast, and that could go up to 20,000 messages per second. Yeah, well, it is fast, 20,000, good number. Is it really fast? Well, actually, it was 20,000 running 100% of CPU. This is important to say. So is it really fast? Is it something fastish, slowish? What does fast mean? Well, I don't know. Stuff can always go faster. In fact, I believe that Node could go faster, and I could be able to handle a lot more things. Well, I went down the rabbit hole of performance optimization. I hope all of you had at some point in your life. It's quite a nice rabbit hole. I was there, and I was with my friend Trevor Norris, and he showed me some tricks, and I learned a lot. And yeah, I set myself a nice goal of achieving a 10 times boost on my broker. I wanted it to go from 20,000 messages per second to 200,000. So let's start my old broker, and let's see how it now performs. So I have a nice script called bombing that goes down and sends as much messages as it can be sent. And in fact, well, you see it's ticking at 20,000 messages per second. Yeah, let's try the new one. And let's see how it goes. Well, we need to run a little bit patched version of Node. We'll talk about this in a moment. And so this is the new broker ticking. And hopefully, it's ticking at 200,000 messages per second. Yeah, 200,001 messages per second. So I achieved a 10 times boost on performance. So you see this ticking at these nice little numbers. There is one more 0 in there. So yeah, well, this whole talk is all about how you can make your code run that fast in Node. And anybody that says that Node is not as fast as Go, or Node is not fast, or whatever, don't really believe them. So what tools did I use to make this journey? First of all, flame graphs. I tried flame graphs. Flame graphs are amazing. I tried dtrace for flame graphs and some other stuff. I tried MDB. In fact, the only thing that worked for me was this little bunch of options that you can pass to the V8 interpreter in your node, and that tells you what it's doing about your functions. We'll see those in a moment. So let's start talking about how the event loop works. The event loop is a really nice thing. Basically, when we execute some JavaScript, we schedule some asynchronous I/O. And from that asynchronous I/O, we got an event in the event queue. And then we got back into our event loop. We execute some more JavaScript, which returns to some more async I/O, possibly. There's also a thread pool for stuff that cannot be done in our that can be done by the kernel async I/O level. Well, what does fast mean, and how we can get faster? So fast, for me, it means that we can do more I/O. I usually write applications that I want to drive a lot of I/O out of them. I don't want to write a high-intensive calculation system in Node or anything. I mostly do I/O applications. So I want to do applications that can do more I/O. This is fast for me. So basically, we need to get an I/O event and then process that event, because that's what it is. Like, we have an event loop, we process that event, and then we need to release the CPU as fast as possible. This is how to get fast. Release the event loop as fast as possible. So another event can come in, and we can handle that. So all this boils down to your JavaScript and to your V8, OK? It all boils down to JavaScript and how your JavaScript is working. So V8 is really good, and it can optimize our functions. It can make our functions run insanely fast. However, they need to run enough time. V8 is smart. It looks at how that function is being running, and it optimizes it on the fly. So this process is called optimization. So that -- trace opt options will get that fast, will get your function fast. However, in Mosca, I was allocating a lot of closures and a lot of functions. Those functions, given that I was allocating a lot of them, were not running enough time for V8 to being able to optimize them. And most of them, in fact, were anonymous. And the best recommendation I can give to anybody here writing anonymous functions everywhere, stop. Start putting name in your functions. In fact, this is my enemy, my first enemy. When you run with -- trace opt, you will get this nice output saying that there is an anonymous function that is available at some address over there, and that is suitable for being optimized and recompiled by V8, but says nothing about it. And then this function address goes away because it gets collected by the garbage collector. So it never gets optimized. In fact, this boils down to this pattern. I hope all of you have seen this pattern in your life and use this pattern everywhere in your code. And this is what's making you slow. So, well, I have a little bit of code time now. Hope everybody in the bottom can see. If you don't see, come back forth. So basically, we can show a little bit of things. So the first stuff I want to show you is doing some really dummy parallel call. So in all your code, you might want to execute a bunch of functions in parallel. This is normal. And those functions that you execute in parallel in series or doing whatever operation on them, well, what you possibly use is something like async or promises or something like that to run those. So the most naive implementation for running a bunch of functions in parallel, the most fast naive implementation is this one. Basically, we have a for loop, and we call all those functions and allocating one single closure for all of them. OK? So we can run this nice little thing against us very easy set immediate stuff. And in fact, you can see that the naive thingy is a little bit slower than the set immediate one. A little bit, 10%. Well, we can get it better, and we can use a library that I wrote called Reusify. There are a lot of different intermediate steps, but we're not fitting the length of the talk. Sorry, guys. Reusify allows you to reuse a closure. So we have seen that allocating a function is expensive. It's an expensive thing to do. So I don't want for every parallel allocation in my code or for every series allocation, for every series call or waterfall call or whatever I'm doing with asynchronous. I don't want to allocate functions. So with the Reusify, allow you to reuse a closure. How you use it? Well, you actually call it passing a constructor. You need to pass a constructor because a constructor can be really optimized by V8 using a thing called hidden classes. So basically, it gets super optimized by V8, this class, so it can look up properties really quickly. And basically, what we are doing here, we are just wrapping that in a closure, maintaining a very small closure scope. So using this, we can avoid allocating the wrap call down here. So if we run this guy, this little benchmark, which will run the previous one as well for easiness, as you can see, the numbers are slightly different because there's some stuff running on my laptop. As you can see, the Reusify is slightly faster than the naive implementation. It's still not super OK. Well, I have some more stuff to show. There is a nice benchmark thingy that benchmarks parallel for a lot of stuff. And in fact, I'm not running this benchmark because it takes a lot of time. And well, this example has this URL. I've run the benchmark and get a screenshot of it. And if you look at it, basically, you can see that over here, there is the naive faster. Well, the set immediate takes even 17 milliseconds to run 10 million set immediate call, and the naive implementation can increase it for 2 seconds. And in fact, using reusify, we boil it down. We shove down 1 sec. And then the implementation with reusify, it's wrapped in a library called fast parallel. As you can imagine, that's the same thing that I showed you, which adds some more checks. And those checks takes time. And I added another library wrapping all the content of this talk called Steed. And these are some more safety checks, safety nets on arguments and parameters and so on, which is even a little bit slower. Just for comparison, if you use async, how many of you use async in this room? Yeah. So async on the same benchmarks take 34 seconds versus 20. Okay? So this is what async, the overhead async is causing you, is slowing you down. There is a nice library called neoasync that is fast, and is as fast as my library. However, there is one catch, and I will show you in a second. So given that we can wrap, given that your reusify allow us to wrap it in, create some, wraps it in some state, we can actually use it really nicely. So as you can see here, so you get your, you see there is a map operator as it's there in async. So with Steed.map, you can pass it a first object, which is the state. What is the state? The state is another class, as I call it. It's another little older that just maintains some context out of our code. Basically, we are creating our own closure. If you look at how libuv does things, I hope all of you knows what libuv is. If you look at how libuv does things, it is almost the same, very same pattern of operation. So you can pass in your state, you create your own state, which you manage your own closure, basically. Pass the parameters to be called, the array of which to apply the map operator, and then we call multiply and done. Just for comparison, before I enter the internals of the code, this is the implementation using async. If you look at, this is how you will usually done it using async. You have some closure stuff. You have some parameters that comes from our main function, some arguments, and we wrap them in a work operator. And then we have some function. We have a function that is called when things are done. This is a pattern that is almost common in every piece of code using async. Okay? And instead, with Steed, you can actually write them as top-level functions. So if you run them as top-level functions, what it happens is those functions can be extremely optimized by V8 when they run. And this will cause you a lot of big speed improvement. In fact, if you see that we have multiply here, and we have done, and in fact, we are actually using this dot factor, which is basically our factor thing that we are passing it in here. Oh, yeah, this is a bug. Let me fix the bug. Yep. So basically, this is what it is, OK? And we can actually call this.cb and this.cb here to call our callback and process things. So let me show you how this perform, because it's quite nice to see how this perform. And if you see this is Steed, it takes 1 million calls, 3 seconds. And this is neoasync. It's not double in speed, but it's close to. Just for comparison, let me show you how this works with async, because it's quite nicely. I cut it because it took too much, but I have time now, so I was running so fast. And I can actually copy this over and just replace it. And using async is actually quite interesting because it's super slow. When I mean super slow, I mean super slow. And yeah, let me show you, because it's actually unbelievable, the speed difference. And you are using async, so your code is way slower than it should be. I'm a little bit obsessed about performance, so as you can imagine. So this is Steed. And then there is Neo. It takes 5 seconds. Hope it doesn't crash. Oh, yeah. Well, async is slower. OK? It's twice as fast as async. Oh, yeah, whatever. It's something that is running on my system. That these numbers, you need to run these numbers for a very long time. So a nice thing to show you is about this is to show you the. So let's just watch what async is doing using the options. So I'm commenting stuff, and I'm running trace opt, trace inlining, and trace deopt to my map thing. This is what it's doing, OK? You see my enemy over there, OK? All those functions being allocated for recompilation and never being optimized at all. This is what's happening to your code if you use async. If you instead, let's see what Neo is doing, because it's quite interesting to watch it. And yeah, we can run the exact same thingy. And again, it's allocating stuff. Less than the other one, but still a lot. And let's watch what Steed is doing instead. Yeah, a little bit. What's the problem here? Yeah, but it's not what it is. Whatever. Yeah, as I say, there is still room for improvement. Yeah. So basically, yeah, why is it doing that? Wow, big question mark. So, yeah. Yep, again, code time, I show you this. And yeah, the examples are over here. This is the library, this is Steed. Check it out. Again, let me replace this to you. You can pass a state function. This is optional, of course. The state is optional, so you can use it as before. But it will be way faster if you pass in a state and use that. You need to allocate it. See this, guys? This is important. You need to allocate it because it's reusing functions. It's reusing code. So you want to have a fresh instance every time you use it, basically, for every of your modules. And yeah. So Steed has some nice stuff, each map series, parallel, series, waterfall, queue. So rules for hot code path, well, do not allocate any functions. This is the first thing you need to do. Do not allocate any functions in your code. Make sure that V8 can optimize them. The second bit, really important. When you are 100% of CPU, everything is hot, because you are in an event loop. So even if something that runs once in a while, that can slow you down. Make sure. There is a missing bit here, which we didn't consider, the garbage collector. This is actually my real enemy. In fact, when I was developing the new version of Mosca, I was allocating a new buffer for each packet and copying all over the information in the packet, which takes a lot of time. Moreover, those buffers need to be allocated after the fact, because I just generate them and throw them away at high speed. Solution to this is do not allocate a packet at all. Stream the packet generation write the packet generation directly to the stream. So you can write all your packet as soon as when you can, instead of allocating it and copying the data inside the buffer, you can actually write stuff down and avoid all possible allocation. You can memorize I was able to memorize the headers. So if you don't know what memorization is, I hope you should. Look it up in Google if you don't. And basically, I was able to not allocate them and cache all those headers, so I don't have to allocate those buffers for the headers every time. Again, it doesn't save you time to not allocate them. It saves you time when the garbage collector needs to collect them. In fact, all this makes sense, only starting Node 12 going forward. Without Node 12, you can't really use any of this because you don't have the cork and cork API. If you don't know what cork and cork is actually an amazing piece of technology inside the stream API. And basically, you have a write stream, and you can cork it. You cap it. And all the writes will be buffered down. And when you uncork it, all the writes will be passed through the to the next stream or to the C++ layer beneath it. So basically, you are able to send a bunch of writes, and then call cork, send a bunch of writes, call uncork, done. Is actually extremely, extremely fast. So like second path of the rule for hotcode paths, GC time counts a lot. Allocate as few objects as possible. From time to time, it's OK to use slow code that doesn't allocate. So my streaming packet generation thing is half the speed of the one that was allocating buffer. However, I needed to increase the time and put it through some I/O to get the real difference. From time to time, some slow code that doesn't allocate makes more sense. Yep. And yeah, after this, I applied all this process, running benchmarks and seeing what was the output to Node. I found a perf bug in Node, performance bug in Node, which makes all your stream 5 to 50% faster when you write stuff to them. Yeah, in my case, it was the last 10%. This is the pull request, still not merged. Hopefully, it will be soon. Check it out. Give me some feedbacks. Try it. See if it doesn't break your stuff. And yep, all your HTTP requests are streams. So you probably want this. And yeah, remember that most code doesn't need to run at ludicrous speed. Just normal speed is fine. Light speed is fine, again. Ludicrous speed is a little bit dangerous. Check it out, my library, Steed. And this presentation is available at a couple of URLs. So if you want to take a quick picture, if somebody, or they will be published on by the guys of the conference later on. And then, well, that's all of it. That's me. I do a bunch of open source stuff, maintain a lot of libraries, and so on. I'm speaking tomorrow about cocktail robots, if you want to check it out. And yeah, I work for a company called nearForm. We have a nice booth, and we have a whiskey testing. Kian, at what time is the whiskey testing? Half 5. And we have a whiskey testing at half 5 at our booth, so check it out. And come and say hi. I hope all of you like whiskey. Whiskey makes you go really fast, OK? And thank you, guys. Thank you. I have 50 seconds left, and I don't know. Oh, we have a question. OK, yeah. This is faster than Bluebird. Yeah. There is a pull request against Bluebird when I put this in. Check it out. I didn't want to do that too much. It's like 10% faster, 20% faster than Bluebird. Okay, so Bluebird is faster than anything. Yeah. Yeah. Well, you can't get much faster than this. You're pretty close to what Node can do. So, yep.